Welcome once again. Now, in our last video, we were talking about dative covalent bond. We have explained what dative covalent bond is, saying that it is also a covalent bond, except that the electrons that are shared between the two atoms are donated by only one of the atoms taking part in the sharing. The other atom, of course, also does something. It brings its empty orbital to accept the electrons before the sharing can be done. And I've given you all the molecules, examples of molecules where we have dative covalent bonding. So the examples we gave were one, hydrazonium, where we have the bond between water and hydrogen ion. We have two, ammonium ion, where we have bond between ammonia with one lone pair electrons and hydrogen ion. Three, I give you examples of water and BX2 compounds or BX3 compounds, where my X here is hydrogen or halogen. Then we have ammonia. When I write ammonia, I don't say that it is not ammonia. NH3 or H3, and it's the same thing. I just want to show it here. So this and either this or BX3 compounds, where beryllium and boron are atoms that exhibit covalent bonding but have empty orbitals in the p orbitals of these atoms. So these are examples of dative covalent bonds. Now today we are going to look at, the next thing we are going to look at is nonpolar. Compound or bond. And then we'll also look at polar covalent compound or bond. What is nonpolar covalent compound or pure covalent compound? Polarity we have explained already, that when there's separation of charges, then we say that substance in chemistry or in science we say it is polar, where we have one end being negative or another end being positive. That is all we mean about polarity. Now, so if we say a bond, a covalent bond is nonpolar, it simply means that it is a bond in which the covalent bond is such that the atoms are equally shared. Sorry, the electrons are equally shared between the atoms that are sharing the electrons. Remember that a covalent bond is a shared pair electron between two atoms. We are still on covalent bonds, and so anything that we are doing will refer to that covalency. Covalency simply means sharing of electron pair. So when we say something is nonpolar, we are calling it nonpolar because the two electrons that are going to be shared are equally shared between the two atoms that are taking part in the bond. Where there is some sharing, one person decides to take a higher percentage of the two electrons more onto himself than the other, then where the electron shifts will be more negative than the other side, which will have less electrons, and that will be partially positive. So some polarity will be introduced into the bond, and then we say that will become a polar covalent bond. So that's the difference between the two, nonpolar and polar. Nonpolar simply means that there is equality in the sharing. Polar means that there's inequity in the sharing. So we define a nonpolar covalent bond as a type of covalent bond where two atoms equally share a pair of electrons with each other. Be careful, students make mistakes on this. The nonpolar is equality. Okay? Nonpolar means that they are sharing it equally. So the two electrons are equally separated. One here. And so there is no separation of charges. Okay. The polar is a type of covalent bond where the pair of electrons is unequally shared between the two atoms. One is greedy. I wouldn't call it greed. In chemistry, we call it more electronegative. What is electronegativity? The ability of an atom to pull share pair of electrons more to itself than the other atom. That is electronegativity. It has higher affinity. It has higher zeal for electrons than the other atom. And so even though the electrons are supposed to be shared between them, it will always be, at all times when you go, more of the electrons will be on this side than the distance. Just like you and your senior bring your galley and milk and other things together to come and share. Definitely the senior will take a fair share than you. Okay? The senior will take a fair share than you. So polar covalent substances always have to do with two different atoms when they are sharing a bond, when they are sharing an electron. Definitely, because the two atoms are different, one will have a higher electronegativity than the other, and will pull the electrons more onto itself than the other, and the bond will perpetually remain polar. But where we have the two atoms being the same, hydrogen, for instance. So let me explain them better. This one, example, is for homonuclear diatomic molecules. Homonuclear, remember we have defined all these same types of atoms. Hydrogen, oxygen, okay, chlorine, nitrogen. In all these, when they form bonds, ideally the atoms will be said to be equally shared. The electrons will be said to be equally shared between the two atoms. This is a hydrogen atom, each one bringing an atom. When they share this, ideally at all times it is expected that these two electrons will be equally shared among the two. Now, if these two electrons are equally shared among the two and they all have their duplet, what kind of intermolecular force will exist between this molecule and another molecule here? Okay, but it is assumed that when you have hydrogen molecule, or you can put them together in a bottle or in a glass and they exist and play around, when you release them is when they'll be separated. That means that there's some intermolecular forces. This is where Van der Waals comes in. It is Van der Waals who identified that type of force. And so the intermolecular force there is named after Van der Waals and it's called Van der Waals forces. But under Van der Waals forces, where you have the same thing for the nonpolar, where you have the same thing, the type of force that he describes is called induced dipole. So this molecule and that molecule, a force can hold them together. That is why when this molecule is moving in this direction, this one will also move in that direction. If there's no this force, if this force doesn't exist, why should this molecule follow this when they are going? Each one should go its way. Hope you understand me. But when you put it under X-ray, release a gas, you see them all moving in one direction until such a time that the bond breaks and then you see others moving in another direction. So for all homonuclear diatomic molecules, same atom diatomic molecules, the bond between the two atoms, that is the intra, is a covalent bond, but the inter is said to be a weak Van der Waals force. The actual name is called induced dipole. Induced dipole force. Okay, I'll explain this in my next video. I just want you to know that the bond between this molecule and that molecule has a force holding them together, and that force there, you can say it is weak Van der Waals force, or you can say it is induced dipole. They are all accepted. Now for the polar ones, let's take a molecule like HCl. Definitely, hydrogen has a very low electronegativity compared to chlorine. And so when these two electrons, hydrogen donate one and chlorine donate one, and they share, there is no point in time that you go and find all the electrons equally shared among the two. The chlorine, being more electronegative than hydrogen, will always pull the electrons more onto itself. And when it does that, it will have partial negative charge, partial positive charge at all times. When this happens and there's the next molecule close to it, automatically this and this will attract each other by electrostatic force of attraction. And that electrostatic force of attraction is again called a dipole. This is, it's already polar. So there is no any inducement. So this is called dipole-dipole interaction, also explained by Van der Waals. So Van der Waals forces have two types, dipole-dipole interaction as well as induced dipole interaction. Of course, here too, we should indicate the negative, and then this will be positive, so that they can attract. If it is negative and this side is positive, so it means that here this will also be, if it is, yes, positive. Okay, partial, very small ones. So in some books we indicate this symbol is used to indicate small. So if I put two of it, then it means they are very small. Okay, that is smaller than the one with one. So here, when I put two of this positive, two of this negative, it means that very small negative charge there, very small positive charge here. When we come here, this will also be polarized in the same way. Very small positive, very small, sorry, very small negative. No, negative, positive. This will attract this one by positive, so positive here. And this will be negative. So that they can attract each other by that very weak electrostatic force called Van der Waals forces. This one is, this and this are already polar because of the difference in electronegativity between hydrogen and chlorine. So this bond here is called dipole force or interaction. The chlorine molecule, I use hydrogen on the whiteboard, but here by this diagram it is using chlorine. Chlorine atom held by this covalent bond, equally shared. Okay, chlorine atom held by this, but there's a force between this and that. And when you come down here, there's also going to be a force between this and that. Now that force here is called induced dipole interaction. But these bonds are covalent bonds. They are covalent bonds. So that is an illustration of what this thing is. Now, when we come to the one that I've explained already, that is a dipole-dipole interaction. This HCl is already polar because the chlorine is more electronegative than the hydrogen. So this will have negative charge, this will have a positive charge because it draws the electrons more into itself than this. And so if this side is negative and that side is positive, then this bond here is not any inducement, but it exists as a polarity on its own. Therefore, dipole-dipole interaction. Over here too, you can also have the same thing. Chlorine, HCl, here HCl. I mean hydrogen, chlorine, all the bonds there will be dipole-dipole interaction. That is the intermolecular force. But the force between the molecule will be covalent bonds. The force here is covalent, the force here is covalent, the force there is covalent, the force here is covalent bond. Now, why do we call the other one induced dipole? We call it induced dipole because it is an assumed polarity. That assumption is based on the fact that electrons, we say, are mobile. Electrons can never be stationary. So though this hydrogen, or if it is the chlorine we saw on the other board, is supposed to be, the two electrons are supposed to be equally shared among them. Because electrons are mobile, there's a probability that at a point in time, a fraction of a second, you can have almost all the two electrons shifted on one of the atoms. At that instant, we say there is a temporal dipole. Because when these two electrons, because of the virtue that they move together, they move around, are shifted onto this, at that instant, this one becomes negative. At that instant, this one becomes positive. when this happens, it can, because it's closer to it, it can induce this one to also become polar in that same manner. That is when they attract each other. So when the electrons, within another fraction of a second, when the electrons are now aligned to this bond will definitely break. And that is when you see this molecule moving here, this molecule also moving there. So induced dipole is so called because it is a temporal polarity that is established, or that finds itself in a molecule where you have two atoms having the same electronegativity. So we call it induced dipole interaction. Basically, my attention for this video is for us to know the difference between nonpolar and what? Polar covalent bonds or substances. Here, my brothers and sisters, I've used only two atoms, showing one bond and then intermolecular forces. What about if there are several or more types of bonds in the molecule, like ammonia, for instance? Ammonia. H. This is how the structures will be. Is ammonia here? Yes. Ammonia is here like this. Okay. Hydrogen. Nitrogen is here. Nitrogen. Which is more electronegative. Nitrogen is more electronegative. So to put the electrons here, to put the electrons here. Movement. In chemistry, it is not only physics in physics that we do vectors. In chemistry too, we also do vectors. So to be able to determine for more than two atoms, to be able to determine whether a molecule is polar or not, we apply certain concepts when we come to hybridization. And so that is the next major topic that we'll be doing. Carbon dioxide. This is carbon dioxide. It's here. Carbon, oxygen. Is this polar or not? We'll know whether it is polar. This is a nonpolar molecule. This is nonpolar. I'm only telling you. Why? Because whatever you have here exists here. So whilst this oxygen is more electronegative than the carbon, so while carbon is pulling the electrons here, while this oxygen is pulling the electrons from carbon here, this one is also pulling from here. So the vector sum, the force here equals this force here. So this molecule in chemistry will say it is nonpolar. Okay? So we use several concepts to determine whether a compound is polar or not. And it is only when we are able to tell whether a compound is polar or not, it's when you'll be able to tell the intermolecular force in it. Because if it is nonpolar, then we expect it to have weak van der Waals forces. And this will tell us, if it has very weak van der Waals forces, then it will tell its melting point, boiling point, and all the others. That is why we are hanging on the physical properties, unless we understand all these concepts before we apply to our physical properties. If a molecule is polar, the intermolecular forces there is going to be dipole-dipole interaction. Dipole-dipole interaction is stronger than induced dipole interaction. And dipole-dipole interaction is also weaker than hydrogen bonding. We have not done hydrogen bonding yet. We'll do it very soon. Okay? And of course, by this, we'll classify all the intermolecular forces, their strength. The first one being covalent bonds, covalent network. That is why diamond and these brothers are the strongest. From there, you come to ionic or electrostatic. So some ionic substances are stronger than some metallic, but the metallic are also intertwined. So metallic bonds are also electrostatic, but they are also stronger than ionic bonds. So from covalent, we come to the metallic, then you come to the or those that are electrostatic before you come to hydrogen bonding. And remember that we said that molecular covalent substances or semi-covalent substances, all of them may have only hydrogen bonding or van der Waals forces. So they are the least in terms of strength. If they are the least in terms of strength and compactness, then it means that they will be the least in terms of boiling point and melting point. But among the least, those with hydrogen bondings they are stronger than those with dipole-dipole interaction. And those with dipole-dipole interaction will also be stronger than those with van der Waals forces. So this is why we are studying all this. But at this point, I'm not going to be able to teach you all molecules, but all the several molecular covalent substances, whether they are polar or nonpolar. You cannot just use atom A and B and say that, yes, I know this is more electronegative than this, therefore there will be polarity. Like for instance, if you take like carbon dioxide, someone say, because it's carbon and oxygen, and carbon is less electronegative than oxygen, then I think it should be polar. If you did that, you are wrong. You have to consider the shape. The shape of carbon dioxide is linear. If I say linear, it's like this: carbon, oxygen, carbon, oxygen. So if it is linear, the draw or the pull of electrons from the carbon to this oxygen is the same as for the pull of electrons from here to here. So the effect here will cancel the effect here, and this will become nonpolar. But assuming it is carbon monoxide, it is only one side. If it is carbon monoxide, then it's just carbon, oxygen. So the pull is only on this side. So that will be polar. So I'm introducing another concept. Polarity or non-polarity depends on one, the electronegativity, and two, the shape of the molecule. The shape plays a very important role. If the shape is symmetrical, if I say symmetrical, where you can divide exactly and this, and where it is symmetrical, then the symmetry comes in, it cancels the effect of the pull of the electrons, and the compound becomes nonpolar. But if it is not symmetrical, then it becomes what? Polar. So I would end this topic here. Now that we have studied dative covalent bonding, now that we have studied polar and nonpolar covalent bonding, we'll be able to look at physical properties of covalent substances. So come with me in the next video whilst we consider the physical properties of covalent substances. Of course, this topic will also be treated under whether they are covalent or giant, they are simple covalent or they are giant covalent substances. Thanks.